Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. Excuse me. And today we are finishing the notes for AP Chemistry, Unit 9, Thermodynamics, and Electrochemistry. Yay! So when I had my YouTube channel before I taught here, and I would finish the classes, I had this special hat I would wear for the last video of the class, and I forgot my hat. I was going to wear the hat today. It's like all crazy. It's a Jester's hat I got at Six Flags a long time ago, because you know I love Six Flags. So anyway, you can pretend I'm wearing a hat. I probably have like some crazy headband I can wear. Let's see if I got one. Ooh, I got reindeer ears. We can wear that. That's pretty good. Let's see if it even shows up on the video. Nope. It's too tall. It ain't gonna work. Okay. Oh well, I forgot my hat. That's how life goes. Okay, so we're going to be talking about thermodynamics and electrochemistry. And I told the other class that this is my 15th, 16th year teaching public school. And when I used to teach in Cobb County, I had a poster, like how there's the periodic table hanging on the wall. There was one I had for electrochemistry, which you've got the poster as a chart in these notes. And I would hang it up, and every year I would say, this year in honors, we're gonna make it to electrochemistry, and we're gonna use that poster, and we never did. And even with this being, teaching AP multiple times, we were running out of time before I reorganized by the AP classroom way. I was spending too long on certain things, and we didn't get to electrochemistry. So this is it. Today's the day I've been longing for over a decade, to get to finally teach electrochemistry. I wish I had the poster. Nobody else was using it. I should have just taken it with me when I left Cobb County, but I didn't take anything. I didn't take a paperclip that wasn't personally mine. So the poster is probably got thrown away because it was really old. But today we're going to finally get to teach electrochemistry. A dream fulfilled for me. Okay, so let's review entropy. The symbol for entropy is delta S. And then, just like Maxwell said, it is a measure of disorder or randomness in a system. That is a useful definition. Now, there's another one that to me is not useful at all. It reflects the quantity of possible energy states in a system. That's just gobbledygook. Who cares about that definition? That's the good one. I like that one. Okay, because that's the one that I can use to answer questions on the AP test. Because they're going to ask me what has high entropy and what has low entropy. And we can see here that solids have lower entropy than liquids, that have lower entropy than aqueous solutions, that have the lower entropy than gas. Gas has the highest. Now notice, you need to remember that aqueous is considered more disorderly than liquid because in liquid it's just one thing in the liquid state, but in aqueous solution it's more things all mixed together, being a little more chaotic. Can you see that? Or you need to know that low temperature systems have low entropy, and more order, and high temperature systems have more disorder, high entropy. But what if everything else is the same? It's at the same temperature, it's in the same state of matter, and you are asked which one has higher or lower entropy. The answer is the one with less particles have lower entropy. The one with more particles have higher entropy. More particles, more things to be disorderly. Okay? And then here I've got a building that shows good entropy here, that we have built versus destroyed. Built is low entropy, destroyed is a high degree of disorder. And you can think about it would take a lot of energy from an outside force to go back from disorder to order, wouldn't it? Okay, so one of the things you'll be asked on the AP test is questions about which has more entropy. And do you feel ready for that question? Good. All right. So, what about charges? If entropy increases, it is a positive delta S. If disorder increases, it's positive. If disorder decreases, it's negative. So with that in mind, this is another thing AP could ask you is, would the entropy for these situations be positive or negative? We're going from aqueous to solid. Is it going to be positive or negative? Somebody said it very softly. It's going to be negative, because if disorder decreases, it's going to be negative, and to go from aqueous to solid, it's getting more orderly. It's getting a nice little crystal lattices. Okay, what about going from solid to gas? Is that going to be positive or negative? Positive, because it is getting more disorderly. Here it's all gas, it's all at the same temperature. Is this one positive or negative? It's negative, because we're going from 3 particles to 2. So it is negative. It's getting more orderly going from 3 to 2. All right, that was section 1. Section 2, absolute entropy and entropy change. So this is the formula for calculating delta S. It's you add up the products, multiply them by their coefficients, add up the reactants, multiply them by their coefficients, and then it's products minus reactants. We've seen formulas like this before, haven't we? Very similar. This is also in your AP reference sheet that you will be given. Remember, the Greek letter sigma, very fancy. It just means add stuff up. It's the summation symbol. It just means add them up and then subtract. So, and it's very similar to the delta H formula we already learned. So here's an example problem. We have this solid plus gas makes gas and gas, and we are given the enthalpy. Sometimes they're in a chart and you have to look them up, and they're given to us. We multiply them all by their coefficients. We add up the products. We add up the reactants. We subtract. And I already did the math. It is 133.78. And this is Joule, mole, Kelvin. And these are the ones are coefficients. Okay? Two sections down. 9 to go. So delta G is Gibbs free energy and thermodynamic favorability. Entropy is called the second law of thermodynamics. There's 3 ways to say the same thing. Things move from order to disorder unless acted upon by an outside force. The entropy of an isolated system will increase over time. And I think Maxwell said that the entropy of the universe is increasing. And also, every spontaneous process increases the entropy of the universe. All of this is saying that things that Mary Poppins is not true. Your room is not going to clean itself even if you sing it a song about sugar. That if it's going to go from disorder to order, it's got to be acted upon by an outside force. Okay? A spontaneous process is called thermodynamically favored process. So let me explain that to you. Back a long time ago, long time ago, in the 80s, when I was your age and taking chemistry, we didn't call it thermodynamically favored or not. We said reactions were spontaneous or non-spontaneous. If they were spontaneous, you put the chemicals in the beaker and boom, they go. Okay, so that's a spontaneous process. Non-spontaneous, that you put them in, they don't go. But now they have changed the terminology, and now they call it, you just put them together and it goes, it's called thermodynamically favored process. You are allowed to abbreviate it, TFP in AP chemistry, or you can just write favored or unfavored, okay? So what this means is if it's thermodynamically favored or spontaneous, it will happen at a certain temperature. Now, we already talked about what drives reactions is enthalpy and entropy. So entropy, increasing disorder, delta S is greater than 0. So if it is favorable for the entropy to be positive, to becoming more disorderly. The universe likes disorder. It goes toward disorder. And so if S is positive, that's more disorder. It's more likely that the reaction is going to happen. the reactions are also more likely to happen if they're exothermic. So that means that H is less than 0. Exothermic reactions are negative, so things are going to happen, reactions are going to happen if entropy or disorder is positive and high, and if temperature is high. That makes things want to happen. If both of these are true, if the heat is a negative number and the enthalpy is a positive number, the reaction will happen. It is called spontaneous, especially back in the 80s, or thermically favored process at all temperatures. No matter what, it's going to happen. If it's endothermic, if H is positive, and if it is moving to order and S is negative, it will not happen at any temperature. It is not thermodynamically favored at any temperature. It's not spontaneous, at any temperature. Now, you can make it go, but it just won't go on its own. And we're going to talk about ways to make reactions go when they don't want to go at the end of this unit. Okay, in general, if both H and S are positive, the reaction is favored at, okay, so this is, what if one's one and one's the other? Okay, if H and S are both positive, the reaction will be favored at really high temperatures. If H and S are both negative, the reaction is only favored at really low temperatures. Okay, so we have a handy chart to help us keep up with this. Here's the handy chart. Okay, if H is negative and S is positive, it is spontaneous at all temperatures, thermodynamically favored at all temperatures. If H is positive and S is negative, it's non-spontaneous at all temperatures. So here is endothermic and moving to order, non-spontaneous. Exothermic, moving to disorder, spontaneous. But if it's half and half, if S is negative, it is moving to order, and H is negative, it's at a high temperature, it is negative, it will be spontaneous at low temperatures. If S is positive, I said that backwards, that was negative. If S is positive and H is positive, endothermic, and positive S, it will be spontaneous at high temperatures. Okay. Don't worry about that T delta S yet. We're going to learn about that in a second. All right, so that little chart a little bit handy. Ethan, stay awake. This is our last one. And it's not going to take the whole period. So you only have to pay attention for a little bit here. All right, next. What about if it's mixed, one favorable and one's not, and you can't tell from just looking at it? So it doesn't fit our chart. One's favorable, one's not. We can't tell by looking at it. We have a formula called Gibbs free energy formula to the rescue. It's a measure of the thermodynamic favorability of a reaction. And we're going to learn 4 ways to calculate it, just like how we did with heat. This is very similar to the heat chapter, which y'all did good on. So here's our first equation. The free energy is equal to the change in heat minus T delta S, that's temperature. Both G and H are in kilojoules per mole usually. Temperature is in Kelvin, just like in the gas laws. This is going to be similar to the gas laws in some ways too. And entropy is in kilojoules per mole Kelvin. So what does that mean? If G is negative, it is favored. It's going to happen. So G looks at S and H and decides, is it really going to happen or not? If G is positive, it is unfavored. So if G's signs are the same as H, and S is opposite. G and H are the same. Negative is good, it's going. S is opposite. Positive, it's good, it's going. Okay. So how do we calculate these? This is our first way. You determine the change in enthalpy, delta H. This is either given to you or you might have to solve for it, like using Hess's law. You determine the change in entropy. It's probably going to be given to you. You convert the temperature to Kelvin if it is in Celsius, and then you plug the values into this formula, and you find the result. If G is negative, it is spontaneous, it is favored. Just like I told you, it's just like heat. If G is positive, it is unfavorable. If it's 0, it is at equilibrium. So this is the new knowledge, put a little star by that. If G is 0, it's at equilibrium. Okay, ready to move on? Anybody need more time on the screen? Okay, so here's an example problem. Water being zapped into hydrogen gas and oxygen gas, but it's actually water molecules as a gas. Okay, so we are given delta H. Notice it's endothermic. We're given entropy, it's positive. So this one is not favored, this one is favored, and we got this temperature. It's in Kelvin, so we're good. But our heat is in kilojoules and our entropy is in joules. We need these all to be the same so we can mark out units. So step 1, I need to change these kilojoules to joules by multiplying by 1,000. Okay, now I'm ready to put it into the formula, and then I do the math, and G equals positive 185, 837.6. Now, it's positive. Is it favored? Is it going to happen at this temperature? No, it is not. So if they ask you to convert back to kilojoules, sometimes you do, then you would divide by 1,000. So this is not spontaneous because G is positive. And that's how we can know if it's really going to go or not. Is it going to be spontaneous? Sometimes they'll then ask, well, what temperature would it be favored at? What you do is you make G equal to 0, and then you solve for T. And so if we did that, it's 5.9 Kelvin. Okay, that was way 1 to solve for delta G. Here's way 2. Here is another formula. Delta G equals the summation of the heat of formation of the products minus the reactants. This is very similar to the heat problem we did. Remember that? Remember, sigma means added up. That is the Greek letter sigma, and it's just fancy for added up. And then we're going to subtract products minus reactants. Do you remember doing that for heat? Okay, so here's an example problem. We got lead ions and chlorine ions, and they're making lead chloride. So we are given delta GF. Delta GF is the heat of formation, the free energy of formation. And it will be given to you, but that's what the little F stands for. Okay, and so we have this number for lead, we have it for chloride, we have it for lead chloride. Okay, we put our products minus our reactants and multiplied by the coefficients. And that's what the little N was. N stands for like moles, and moles comes from your coefficients. So we put them in and subtract it. It's negative 27.3. Is that going to be favored at this temperature? It's negative, so it will be favored? Yes. I saw nodding heads. Good job. All right. That's section 3. We've learned 2 ways to solve our learning target today of solving delta G. Some reactions, now this was new to me. I'm still learning. I had never heard this term before. Ask my son who teaches at Tech, he had never heard it either. So it says, some reactions are so slow, we can't measure how fast they're going. And if that is the case, it is called being under kinetic control. I had never heard that term. So here we got a car rusting out in a field. That reaction has not reached equilibrium, but it's still going on. And I bet it'd go 100 years. I was trying to figure out how long it would take that car to rust away. And I told y'all about that at Six Flags when I told you about entropy before, that they had cute little covered wagons when they opened. I think it was 72. That was close to 60 years ago. And those chassis are still out there rusting, and they don't look like they're going away anytime soon. I think it's going to take them another 40 years to go away completely. So I'm thinking this car is going to take 100 years to disappear. And the reason why, this reaction is so slow is that it has a really high energy of activation. Very few molecules have the energy to get over that energy hump and react, but not none. Some of them like collide into each other and get extra energy from colliding, and whoop, they got enough and they can go react. But it is a really, really slow reaction. It is not at equilibrium, it's just slow, and it's called under kinetic control. Never heard that term before. All right, learn something new every day. All right, let's go on to 9.5. Take a drink of water. I'm going to scroll first. Okay, 9.5. Equilibrium. So this is our third formula for delta G. All of these are on your AP worksheet. Your reference sheet that they'll give you, but this is way number 3. Sometimes they will give you, maybe you have to solve for K. Now remember, we've learned K of equilibrium, Kc if it's concentration, Kp if it's pressures. We've learned Q, which is when K is in question. We've learned Ksp, which is solubility. We've learned Ka for if it's an acid, and Kb if it's a base. We are very good at solving for Ks, right? So this formula's got K in it. And it's got the temperature in Kelvin, and it's got the ideal gas constant, which I love that this is the same exact number you will be using on the gas law problems. I have taught chemistry classes and taken chemistry classes where you have like 5 different ones of these. And I love it that they are being very consistent, that you only have to remember one R. The R is 8.314. And I'm not sure, do they give you that number on your reference sheet? Somebody should look and see if you have to memorize it or not. Temperature is in Kelvin, just like the gas laws, and you take the natural log of K. So remember, natural log is the opposite of exponents, and remember, a natural log have a base, like base 10 or another base. Well, for natural log, for logs do, natural log, the base is E. It's a number like pi. It is irrational. It goes on forever without repeating. And this is the natural log of the equilibrium constant K. So here's an example problem. We're given a reaction, a temperature in Kelvin. We're given a Kc, so this is a equilibrium based on concentration at 0.18 at 500 degrees Celsius, and we're given R. So there's our formula. We plug it in and solve for delta G. And it is positive, and it's kind of good to write your positives on here, 11,000 joules per mole. Sometimes they'll want you to change it to kilojoules. Is it favored? No, it is not, because it's positive. Now, if K is small, if your equilibrium constant is small, G is going to be positive and not favored, and that makes sense. When K was small, our reactions stayed reactants and didn't go to products, right? So that makes sense, that G is not going to be favored when K is small. If K is big, then G is negative, it's going to be favored, and it's going to have lots of products. If G is near 0 and K is near 1, which is where K is at equilibrium. Okay, so how do we feel about? That was our third way. Yes, sir?
I'm just having trouble keeping track of which K we're talking about at which point, like equilibrium constant or temperature K.
Oh, yes. Equilibrium K. Yeah, we need new letters. Y'all have heard my spiel about this. There are other alphabets we can type into. We don't have to have the same letters mean the same things. There's Russian. They got some funky little letters that we don't use. Think about Chinese or Japanese. You're opening up a whole bunch. You know, Arabic, they look like cursive. I'm not real good at cursive, but I can learn. We could have different, we don't have to stick to just our alphabet. And Greek, that's all we have, is us and Greek. I think it's time to branch out on the alphabets. Okay, we could even use an ancient one like Mayan or something. That'd be fun, wouldn't it? Okay, so next one, free energy and dissolution. I'm on the wrong page. I'm like, where is this? Nope, that's the wrong page too. I turned too fast. Okay, we did that one. We are not there yet. We're not there yet. We need to go on 6. 5, 6. I've lost a page in my notes. I think I'm okay though. I got them out of order or something. Something's on the wrong page. We did that one. How did I lose a page? Okay, I can do it without it. Okay, so remember our KSP told us if things would dissolve or not. Well, G is going to do the same thing. It is also going to tell us if things dissolve. So here we have an equation. Potassium chloride is breaking into potassium ions and chloride, and we have a delta G value. It is negative. Do you think that's going to make it dissolve or not? Negative's good for delta G, so yes, KCl will be soluble. If G is positive, it is insoluble. Since it's endothermic, but since the S is positive and disorder is increasing, it goes from solid to liquid. So let me say that again for y'all. This reaction is endothermic. Usually endothermic reactions are not favored. However, notice how we're going from solid to aqueous. That is increasing disorder. So altogether, it makes it where it is favored. Even though it's endothermic, it's favored. Okay, you followed that? Now what about this one? Here's another one. This is also going from solid to aqueous. It's also endothermic, but it turns out this time that the liquid state is orderly, with the ions being nicely surrounded by the water, so S is negative and it is unfavored. So usually if something is going from solid to liquid, even though it's endothermic, it could be favored anyway, but this liquid is aqueous and it's actually it's really orderly. Think back to honors when I taught you about Mickey Mouse attacks and the water attacks the salt and it surrounds it. Water is very symmetrical. It's why, like, not the molecule, but when it gets into orderly situations. For example, when water freezes, we see its beautiful order in snowflakes. Okay, you follow that? So water can very beautifully and orderly surround something and be orderly in the way it surrounds things in water. And that's what's happening here. The water is surrounding this in a very orderly way. And so even though it's going from order to disorder, this is more disorderly than the solid, but it's still more orderly than normal. The water molecules are just being very, like a kaleidoscope. They're making order in the disorder. Just think of snowflakes. Okay, 9.7, coupled reactions. If something is thermodynamically favored in one direction, it is not favored in the other. So you just need to memorize that. But it's logical. So ice melting on a hot day. So ice is going from order to disorder. This is favored. So would the opposite be favored? Would water ever freeze on a hot day? No. So if something is thermodynamically favored, the opposite will not be favored. Okay, thermodynamic coupling. This is sort of like Hess's law, but you do it for delta G. We're going to take equations and flip them and multiply them and do things like that. And the reason why we do this, there are reactions we want to happen that are not thermodynamically favored, but we can add something to them and make them go anyway. Say it is a reaction that can make you gold. You want the gold. You want to be rich. But it is not thermodynamically favored. If we could trick it into going, we would do that because we want the gold, right? So that's what this is. This time we're going to want copper. We've got copper sulfide and we want copper. We're going to sell this copper. Woo, we're going to make some money. But delta G is positive. It won't happen. Never fear. We're going to put another reaction in here too. We're going to have sulfur combining with oxygen to make sulfur dioxide. And notice, this should have a negative right here. Negative, I left it off. I need to fix that typo. It is very favored. It's negative 300.4. So what you do is you put these together. Your G's add up, and now you add them together, and you add your reactions together. You mark out things that are on both sides, just like we did before. And now we have this beautiful negative delta G, and we can get some copper. We can make it go by coupling it with this other reaction. Okay, 8.9, batteries that we finally made. This is electrochemistry. This is the moment. I've been waiting for it for years. Okay, galvanic or voltaic electrolytic cells, which means cells is what batteries are called in science. They're not called batteries, they're called cells. And we're going to talk about electricity and batteries. Okay, so this unit is an application of redox reactions. Remember, you need to remember Leo the lion says grr. Just remember that. Okay, so here we've got an oxidation reaction where iron is breaking into iron ions and electrons. Electrons are a product of this reaction, and it has a voltage. All redox reactions have a little voltage associated with them. They make electricity. That's why we talked about electrolytes. Remember when we talked about that? And I drew lightning bolts on your notes, okay? So here's the oxidation reaction, and here's the reduction reaction, and we can add them together and we can get our total voltage there. Now this power of oxidation plus reduction, and we'll talk more about actually how this adding happens, and sometimes you gotta flip them and stuff. Okay, so we can use this power of redox to make a battery. So this is like a chemistry battery. This isn't the kind that you buy at the store, but it's sort of like the first kind of batteries they made. And what it is you'd have two kinds of metals, and you put them in an electrolyte solution. So I have a copper stick and an iron stick, and I connect them with wires. And the electrons are going to flow out of the iron, and here we have a little meter showing electricity is flowing, and it's going to flow over to the copper. Well, remember in honors physical science where you studied electricity and you made little circuits, and if the circuit is open, the electricity doesn't go, but the circuit has to be closed for the electricity to go. Remember that? And you had a little switch. Everybody remember that from honors physical science? If not, maybe you had those bathtub toys when you were a little kid, and you touch those two little parts on it and the toy lights up. Did y'all have those? The light up bathtub toys? I have some. I'll bust them out and show them to you during our electricity unit. Okay, so this little thing here is called the salt bridge, and it's not really, so it's like completing the circuit, but it's also making it where the charges balance so that everything stays. Remember, nature likes balance. We've drawn scales on the notes ever since honors, right? Okay, so this is our setup. So over here we have in this beaker 1 molar copper sulfate. And over here we have 1 molar iron sulfate. Here, copper ions are being added to electrons, and it is making copper metal. Over here, we have iron metal that is being dissolved into iron ions and electrons. So right over here, this iron metal is getting dissolved, is letting go electrons that go across this bridge, and there's our electricity flowing. Then the iron that was part of this that let go of its electrons now is floating in the solution as iron ions. Okay, everybody got that so far? Over here, you've got copper ions in the solution. But because of this redox reaction is going on, the copper, as these electrons flow over here, these ions are being added to the electrons, and it's causing copper to get deposited onto this stick. So this stick is getting more, it's getting fatter. It's getting more copper on it. This stick is getting thinner as the iron gets dissolved into the solution and its electrons go over there. Now this stick is called the cathode. This stick is called the anode. So over here at the cathode, reduction is going on. Because remember that here we are gaining electrons, so it's reduction. That's our GER. Over here, iron is losing the electrons. That's our LEO. Okay, so over here, oxidation is happening. See how the iron is losing its electrons? So there is a way to remember this. I didn't make this up. Everybody knows it. It's like Roy G. Biv, Castro Bear, PMS, all of those. And it is red cat. So reduction is at the cathode. So you need to color this little kitty red in your notes. Red cat. And then how people remember that oxidation happens at the anode is anox. Well, I didn't have an ox stamper, so I drew horns on a goat. You have to try to make this look more oxy if you can. Maybe get rid of this beard would help. Okay. So here the copper is growing. So, and here the iron is eaten away. And how people remember that is the cat gets fat. The cat gets fat. So I really should have had a fat cat there. A red fat cat. And then we can remember it. Okay. Next. So electrons move from the anode to the cathode. They always are moving from the anode to the cathode. And how people remember that is AC, like air conditioning. But I thought it would be more fun to remember it AC/DC and draw a little rocker dude. But you can remember air conditioning if you want to. But I thought the little rocker dude was funny. And so I put him on there instead. So the salt bridge is so ions can flow and keep charges balanced. Nature likes balance. Okay. Anions gravitate to the anode, cations to the cathode. So that might help you also remember the names of them. Now, galvanic cells, batteries, are always thermodynamically favored. So if you have a battery, you expect it to make electricity, don't you? You'd be very shocked if you had to heat up your battery to a certain temperature or lower the temperature of your battery a certain amount to make it go. Nope, they're always thermodynamically favored. Okay? Now, how do you know which, you've got two metals and you're told to make this cell and you got it going and you don't want to wait to see which one gets fat, which one gets skinny. How do you know which metal is the cathode and which one is the anode? So how you find out is this. Remember the activity series that we used in honors chemistry when we learned about single replacement reactions? That the one on top can replace the one on bottom, but not vice versa. It's the same thing. It's the same activity series from single displacement, and the top one is more easily oxidized. It's the anode. So we need some mnemonic device to remember that the top one is the anode. Y'all get on that. Y'all think of a mnemonic device. We need something to memorize that. Okay, now this was the chart on my wall in Cobb County. So how do you find that? So every half reaction has a voltage assigned to it. How do you know what it is? You look on the chart in your chemistry room if you're in Cobb County, or you've got a little chart and you look it up, or they give it to you. You look it up on a chart or it's given to you, no problem. So see, all of these reactions have a voltage written in. Now they're always listed as reduction, even though one will be oxidation. And so how you figure out which one is the cathode and the anode from the voltage chart is you put it into this equation. And it's that the voltage of the battery of the cell is equal to the cathode minus the electrode, and it equals a positive number. It has to equal a positive number. So you look up the two numbers for the two half reactions, and you see which way to subtract it to give you a positive answer. And that's the correct way of which one goes first and which one goes second, and you know which one's the cathode and which one's the anode. Does that make sense to you? One way will give you a positive answer, one will give you a negative answer. The right way is the way that gives you the positive number. And the overall answer is the cell potential voltage, how much voltage you're going to make in this battery you've made. So, and the degree sign means the little degree, like Fahrenheit degrees. It means just like it did when we did gas laws, it means it is at standard condition. Standard lab conditions, 25 degrees Celsius, pressures are in 1 atmosphere and solutions are at 1 molar. So remember over here on our box, this was STP, not standard oil treatment, but standard temperatures and pressures. So it's the same thing, standard temperatures and pressures. Okay, so here's an example. Calculate the standard cell potential for the redox reaction between zinc and copper, given the standard reduction potentials. So we've got two of them. We don't know which is the cathode and which is the anode. We're going to figure out which way to put them in the formula to get the right answer. So the formula is cathode minus anode, and you have to do it 34 minus negative 76, because what do two negatives make? A positive. So that's going to give us a positive. If we had switched it, it would be negative 76 minus 0.34. That would have been negative. Do you see that? So that's the wrong way. So we know this is the right way because we put it in. And we just get the answer. It is positive 1.10. Now we can write the reaction. You flip the anode, and you can kind of remember that the anode is anti and it's got to be flipped. Okay, so you flip the anode and then you add them up. When you do, these two electrons cancel out, and we've got our equation. Okay, so if the electrons don't cancel out, you have to multiply the equation by a factor so you can cancel them out. So this was 2 and 3. You'd multiply the one with 3 electrons by 2 and 2 electrons by 3, so there'd be 6 and you could cancel out. And that would give your chemicals here coefficients. And that would be the coefficients in your formula. Just like how we did, when did we do this before? We've done this before. Yeah, we did this, like test before last. So also, if they ask you for the sign of delta G, cells are always negative. They're always thermodynamically favored. If you're given 3 materials and asked which to use to make a cell with the greatest voltage, put your 3 voltages on a number line and pick the 2 that are furthest apart. That's another question they ask sometimes. All right, how are we feeling so far? Good. This isn't too hard, is it? I think this is a little easier than your last test. Okay, so cell potential and free energy. Here is yet another. Is this our 4th or 5th way to calculate delta G? 4 or 5, at least 4, maybe 5. Yeah. One more delta G formula, okay? Delta G is negative NFE. This is also given on your AP sheet. So you can calculate the delta G. N is the number of moles of electrons transferred. F is Faraday's constant. We have already learned it. There it is. 96,485 coulombs per mole. And E is the energy of the cell potential. So we can find it for our last example. Okay. So that's Faraday's constant. That's the formula. Delta G is 2 moles. We had 2 moles. Don't forget your negative. Faraday's constant times the voltage that we solved for. And it is negative 212.267 joule moles, or 212.3 kilojoules per mole. Is this favored? It's negative. Is it favored? Yes, it is favored.
Oh, yeah.
Negative is favored, just like heat. Heat is exothermic when it's negative. G is negative, it's favored. Okay, so what about if it's non-standard conditions? What about if the cell is not thermodynamically favored, and what if it's non-standard conditions? So when we do these, we need to remember that electricity is a product of this reaction. Okay, and as the reaction progresses, production slows down and the cell potential voltage decreases. And for example, you've got your cell phone battery, it's going to get less and less, and finally it's going to be at equilibrium, and the voltage will be 0. Your battery is dead. You're going to have to plug it back in. So here is an example problem. The following reaction starts at standard conditions. Calculate the concentration of copper ions for the following reaction when aluminum ions is 1.5. Do you see how that's not standard? Standard is 1, and it's at 1.5. Oh no, what are we going to do? Don't worry. Ice tables to the rescue. Hooray! Okay, so you know how to do these. We started at standard, so we put, so this is, my little thing's got off. There's that one. Mark those. The solids don't go in this, right? So you put little X's there, make it look a little better. Okay, so you start off, your initial situation is 1 molar, but then we ended up with 1.5 molar at equilibrium. So how much did it change? That's easy, 0.5. So it went up by 0.5 over here, but it didn't go down by 0.5 over there because of the stoichiometry. See, this has got a 3 and that's got a 2. So you've got to figure out with the stoichiometry. So this is how I did it. This is a 3-to-2 relationship. So I set up 2 fractions. 3:2 as x is to 0.5. I cross multiplied and solved for x, 0.75. Does that make sense to y'all? Y'all understand what my math there? Okay, so now I put it in over here. X is equal to minus x this time is negative 0.75, and I subtract it and I get 0.25 molarity. And that was the answer to my question, was what was the molarity of the copper going to be at equilibrium? Okay, are they starting to get a little easier after you've seen 100 of these ice tables? Maybe a tiny bit. Okay, here is another equation. This is called the Nernst equation, and it's what we use when the equations or when the conditions are not standard. Now, this equation, they are not going to make you use it on the AP exam. It will be given to you, and they're going to ask you about what happens if you increase the temperature. What will happen to the electricity of the cell? What will happen if you, change Q? What would happen to the electricity of the cell? So this is all goes back to algebra. Remember when you learned about direct and inverse relationships, and you learned that if you had a formula like this, and you increase x, z increases, and that's a direct relationship. But if you increase y, z goes down, and that's an inverse relationship. Remember learning that in algebra class? The direct and inverse. I teach it in Algebra 1 and Algebra 2, so you should have gotten it in one of those classes. If not, learn it in science. I learned trig in physics before I learned it in math, because I was advanced in science and math, but for some reason I just never learned trig. And one day my physics teacher was teaching something with trig, and cosine, sines, all this was on the board. But then he got called out, and we all turned around and said, none of us knew it. And we were all like, what in the world is this guy talking about? What is this that he is doing? Sine, cosine. Looks like it says sin to me. And he's saying that sine, what is this? Sinful math. That's what it is. And then, so there was one kid who had been in a different school, and he said, I know it. And we were like, explain it to us. So he got up on the board and taught trig to us all. Finally, the teacher came back in and we were ready to go. We had learned the basics of trig. And I've always done it the way that other kid in my class taught me to do it. Later, math called out, but I learned that in science first. So if you don't know about inverse and direct relationships, it's okay. You can learn about it today. So that's it. So they're going to ask you questions about that. If one of these things moves, what's it going to do to the equation? And it's exactly like math class. Okay. So E cell is the voltage at these conditions. E little degree mark is standard voltage you can calculate. So these things, they're not going to move. They're not going to say, well, what if the gas constant is something else? No, these don't change. So the gas constant, the number of moles, they're going to leave that one alone. And they're going to leave alone Faraday's constant, of course. So what they're going to mess with is Q, the reaction quotient. That's the same thing as K, except it's a question. We don't know if it's at equilibrium or not. And T is the temperature. They won't make you calculate it, but think about how the variables manipulate it. So if T changes, what happens? It's in the numerator and subtracted. So normally if something's in the numerator and it increases, the answer goes down because it's direct, but this is in the numerator and it is subtracted, so we have to think about that. If temperature goes up, the electricity of the cell is going to go down. If you change the concentration in Q, that can affect it too. If the products increase, the voltage goes down and vice versa. So you're going to do a few of those problems and think through it, but it's just, it kind of makes sense if you just think about. And what I was told to do a long time ago was if you're really stuck on something like the AP test or the SAT or the ACT, and they're asking you questions like this, you can just plug a number in. Plug in 2 and then plug in 3 and see what it would do. And that can fix it. You know, you can just try something because these are just thinking problems. All right, last section. Aren't you excited? Electrolysis and Faraday's law. Okay, way back in honors, I taught you about electrolysis. I said that you have, if you have an electrolyte, that you can use electricity and that you can make silver and gold-plated jewelry, coins, and things like that. And I drew a little fork on there and a diamond ring. You might remember that. Well, this is what we're going to talk about now. Notice this setup is different. It's all in one beaker and not in two. It's not the galvanic cell. This is the electroplating thing. And it's going to have these two sticks going in here. It's going to be an electrolyte. And there it's going to have electricity coming in from an outside source. It's going to be plugged in to be able to do this. So electrolysis is where two electrodes, an anode and a cathode, are submerged in an electrolyte solution. When a voltage is applied, you plug it in across the electrodes. It causes the ions in the electrolyte to move toward the electrodes where they undergo oxidation or reduction and they can electroplate it. So y'all know what I'm talking about. Y'all have seen jewelry before that says it's not gold, it's not silver. And if you took wire cutters and cut it and open, you would see the gold or silver is just on the outside and in the inside it's something else. It's all dull and silver colored. It's not so pretty. They have just made that other metal stick to it. And this is how you do it. So this is the procedure. So this is also called, there are problems that talk about how much. How much metal can you put on your piece of silver or whatever. So these are stoichiometry problems. All we're doing is thinking about amounts, but sometimes we have to use this equation. This is a physics equation. So guess what? Q does not equal what it's been. It's going to be something new. Okay, it's a physics thing. So, but these reactions, they're going to tell us how much we can plate onto something. So we're going to use this physics formula. I is the current in amperes. We abbreviate amperes amps. I've heard of it like with the stereo. Q is the charge in coulombs. Q here stands for charge. And then T is the time in seconds. So here's I equals Q over T problem. 10 coulombs, so that's my Q, of charge flow through a wire in 5 seconds, that's my T. And they want to know what is I. So I divide my Q by T, and I get that is 2 amps. So you could use that formula if you had to. This is like step 1 in the problem. Now this is our real AP chemistry problem. How many moles of electrons have passed through the wire. So we want to find that out. So we use Faraday's constant. Faraday's constant tells you how many coulombs of electrons are in a mole. And it's this 96485. And will tell you how many moles. You just, coulombs cancel out. This is in the denominator. It's hard for me to write fractions on here. 1.04 times 10 to the negative fourth moles. Now, we're ready to do the problem. We got the moles. If you are nickel plating some jewelry using a 10 amp current, providing 36,000 coulombs of electrons in 3,600 seconds, in a solution with nickel, this really should be a Roman numeral, nickel 2 ions, how many grams of nickel are deposited? We want to know how much nickel we are putting in our nickel plated stuff, okay? So there's our equation. Here are nickel ions plus electricity make nickel solid. That's what we want. So this is going to be like a stoichiometry problem. We start off with our number of coulombs, and we want to get rid of them because we want to get to grams. So we're going to try to get to moles and then use molar mass. Do you see where we're going here? So we start with coulombs. We're going to use Faraday's constant as our conversion factor. Coulombs cancel out, and we've changed to moles. Now we use our stoichiometry. We have 1 nickel for every 2 electrons. So nickel goes on top, 2 electrons go on bottom. And then we've got moles of nickel then, and we multiply by its molar mass. You can draw a little M&M around that. And we end up with everything marking off except grams. This is grams right there. Grams of nickel, and we get our answer is 10.95 grams we have put on what we're nickel plating, and it took us almost 4 hours to do that. So it's not a fast process, is it? To get 10 grams in almost 4 hours. Sometimes you have to do this backwards, and they'll give you grams, and they want to know the coulombs. They're just dimensional analysis questions. We did it. That's everything in AP Chem. You are ready for the test now. Let's go. Let's go make those 4s and 5s and 3s. We can do it. All right, science is great.